Welcome back to Very Ordinary Differential Equations. In this lecture, we begin studying power series as applied to finding solutions of differential equations. We're going to be restricting ourselves to differential equations of the following form: linear, second-order, homogeneous equations. But even more specifically, those coefficients p0, p1, and p2 are all polynomials in x. If x0 is a root of p0, that leading coefficient polynomial, then x0 is called a singular point of the equation. However, if x0 is not a root of p0, then we say that it is an ordinary point. If we assume that a solution y can be represented as a power series, there's an important distinction when we're finding solutions between whether the center of this power series is a singular point or an ordinary point. Are we centering the differential equation at a root of this polynomial or not? Now, in finding solutions to this linear second-order homogeneous differential equation with polynomial coefficients, we're going to rely on a very general theorem. Suppose x0 is an ordinary point of the differential equation. In other words, it is not a root of p0 of x, and rho is the distance from x0 to the nearest singular point, then any solution y can be expressed as a power series, and this power series will have radius of convergence at least rho. In other words, if we just find a point x0 that is not a root of that leading coefficient, we are fully justified in assuming the solution y can be written as a power series centered at this ordinary point. So in finding solutions, we are fully justified in saying the solution is a power series centered at an ordinary point, and then the radius of convergence of this power series will be at least as large as the distance to the nearest singular point. Now we're going to get used to these techniques by beginning with first-order equations. So there's not a y double prime term. We just have p0 of xy prime plus p1 of x times y equals 0. Now to find a power series solution y, we're going to go through a few steps. Choose a center for the power series, and we want it to be an ordinary point, so not a root of the polynomial p0 of x. Then we can assume that the solution y is a power series centered at x0. Then we're going to take that power series and simplify the differential equation, p0 of x times y prime plus p1 of x times y equals 0. We now will have a power series that is guaranteed to have a positive radius of convergence because we centered at an ordinary point. This power series is now equal to 0 because the equation was homogeneous. That will generate a recursive formula to tell us values of the coefficients a sub I. And if you have an initial value problem, that gives you some initial values of the coefficients. Combined with the recursive formula will generally allow you to find the exact solution. It's worth mentioning in these problems that if we're restricting ourselves to these first-order equations where p0 and p1 are both polynomials, we can solve these by separation of variables. The equation can be manipulated to look like y prime over y equals negative p1 over p0. And since p1 and p0 are both polynomials, we have a ratio of two polynomials, and we can always integrate these by doing partial fraction decomposition, possibly some sort of trigonometric substitution. This is a doable integration problem on the right. And on the left, we can also integrate this and just get the natural log of y. So this is a doable problem using standard techniques that we already know. But the purpose of these examples here is not that we can't solve them without using power series. It's to get used to using power series to solve differential equations in the simpler context of first-order equations. As our first example, let's find all solutions to y prime plus 2y equals 0 as power series centered at 0. Now note, we don't just have polynomial coefficients, but constant coefficients, so it's pretty easy to find the solution to this anyway. And we would find that the solution is any constant times e to the minus 2x. But we're going to find that same solution through power series. So we do, in fact, have our required form, polynomial times y prime plus polynomial times y equals 0, if we set p0 of x to be 1 and p1 of x to be 2. This constant has no roots. It's just a constant function that isn't 0. So we can center our power series wherever we want, and we're definitely allowed to center it at the ordinary point 0. So here is our solution y, written as a power series centered at 0. Then we can compute y prime plus 2y. So if this is our power series for y, if I take the derivative, okay, the derivative of x to the I is I times x to the I minus 1, but x to the 0 being a constant has a derivative of 0 and simply gets removed from the power series. So the derivative y prime, the power series begins at index 1. And here for 2y, we just have 2 times the original power series. So here's our power series y prime plus 2y, but notice they have different indices. One begins at index 1 and one begins at index 0. Also, the powers don't quite line up between the two terms. The power of x in this first power series is I minus 1, whereas here it is I, and we want to fix that. So we re-index the first power series. Instead of beginning at 1 and having a power of I minus 1, well, this would mean the first power is actually 0, and the second power is 1, and so forth. So if I re-index by making the index match the power, I just have to adjust this I to be 1 larger than this power, and this I to be 1 larger than this power. So with the power being I, these both become I plus 1. But now, both of these series go from index 0 to infinity, and they both have the same power of x. So we can combine these two power series pretty nicely. We add the two power series together and factor out the common term of x to the I. So we just have a single power series going from 0 to infinity. Here is x to the I, so this is now a power series in x in nice proper terms. But our coefficient is no longer just ai, it's I plus 1, ai plus 1. That's coming from this power series here. Plus 2, ai, and that's coming from this power series here. So here is our power series for y prime plus 2y. But since we centered at an ordinary point, this power series has a positive radius of convergence. And since y prime plus 2y is 0, we now have a power series with a positive radius of convergence, which is always 0, and therefore the power series must always be 0. The only way you can have a power series with a positive radius of convergence that's constantly 0 on some interval is for the power series to have all terms equal to 0. So these coefficients, I plus 1, ai plus 1 plus 2ai, must all be equal to 0. For this to constantly be 0, then this power series must constantly be 0. Because we are at an ordinary point, the power series has a positive radius of convergence. So we have a power series with a positive radius of convergence that is always 0. The only way that can happen is for every coefficient to be 0. So now we have a nice expression relating our coefficients ai against one another. So we satisfy I plus 1 times ai plus 1 plus 2ai equals 0. In other words, I can solve this for ai plus 1 and get ai plus 1 is negative 2 over I plus 1 times ai. So we now have a recursive formula that tells us what the value of these coefficients must be. So we have a recursive formula for our coefficients of our power series. ai plus 1 must equal negative 2 over I plus 1 times ai. And all of this was beginning with the assumption that y itself, the solution we're looking for, is a power series ai times x to the I. Those coefficients now must satisfy this recursive relationship. Therefore, whatever a0 is, if I let I be 0, then we get a1 equals negative 2 over 1, or just negative 2, times a0. But what about a2? Well, if I let I equal 1, we get a2 equals negative 2 over 2 times a1. So a2 is negative a1, but a1 was negative 2a0. So overall, a2 is 2a0. If I let I equal 2, a sub 3 equals negative 2/3 a sub 2. So a sub 3 is negative 2/3 a2. But we just determined that a2 is 2a0. So if I plug that in there, we get a3 is negative 4/3 a0. If I let I equal 3, a sub 4 is negative 2 over 4, or negative 1/2, a sub 3. So a sub 4 is negative 1/2 a3. Since we just determined a3 to be negative 4/3 a0, I plug that in here for a3. The negatives cancel. We get 1/2 times 4/3, or 4/6 times a0. So we're ending up with a nice formula being suggested by this pattern. So a sub I was always expressible as something times a naught. And that something was, first of all, a naught is just 1 times a naught, and then negative 2, positive 2, negative 4/3, positive 4/6. If I rewrite these to have numerator 4, this would be negative 4 over 1, positive 4 over 1, negative 4 over 3, positive 4 over 6. So here is a formula that matches everything we've seen so far. Negative 1 to the I, 2 to the I, over I factorial times a naught. Now we can prove this inductively, that this formula now holds for every index I. If you check I equals 0, it's just claiming that a sub 0 equals negative 1 to the 0, 2 to the 0, which is 1, over 0 factorial, which is also a 1. So is a sub 0 equal to 1 times a 0? It certainly is. So this claim that a sub I is always equal to negative 1 to the I times 2 to the I over I factorial times a naught is true for index 0. So let's assume it does hold for some index k. Now we have a recursive formula that ak plus 1 must be negative 2 over k plus 1 times ak. That was the recursive formula we had here. If we assumed ak was equal to negative 1 to the k times 2 to the k over k factorial times a naught, well, now up in the numerator, we have a 2 times 2 to the k, that gives me 2 to the k plus 1. We have a negative 1 times negative 1 to the k, that gives me a negative 1 to the k plus 1. And a k plus 1 times k factorial gives us k plus 1 factorial. So overall, a sub k plus 1 does match our general term. So we have proved inductively now that every term satisfies this formula here. By the way, our original recursive relationship really suggested this. We're always getting a negative, we're always getting a 2, and our denominator keeps getting larger and larger multiples put together down here. So our numerator keeps getting a negative 1 over and over again, a 2 over and over again, and our denominator just gets this product of an increasing sequence, 1, 2, 3, 4, etc., suggesting a factorial down there. So in general, we have established that this formula is true. ai is negative 1 to the I times 2 to the I over I factorial times a naught. So our solution must be given by y is a power series, ai times x to the I, but we just established that ai obeys this nice formula, negative 2 to the I over I factorial, a sub 0, and then times the power x to the I. Notice that a sub 0 is now a constant that can be factored out. Also, we have a negative 2 to the I, x to the I, so overall we have a negative 2x to the I. So if we factor this constant out of the power series and combine these two into a single power, we would end up with this. And you might recognize this now. You have a sum of some scalar multiple of x to the I over I factorial. That is just e to the whatever that multiple of x was. So this is the Taylor series for e to the minus 2x with this a sub 0 factored out. So we've exactly found what we wanted, that the solution y is in fact equal to some constant, a sub 0, some constant, times e to the minus 2x. But we found the solution now through power series. As a second example, let's find all solutions to x plus 1y prime plus 3y equals 0 as power series centered at 0, and then we will find the interval of convergence. Now, since x equals 0 is not a root of x plus 1, that coefficient of y prime, we are in fact at an ordinary point, therefore a power series solution will exist. So we go ahead and set y, our desired solution, to be a power series centered at 0. We can then take a derivative. Remember, the constant term for I equals 0, its derivative is 0, so the constant term gets thrown out when you take a derivative. Otherwise, we're just applying the power rule for derivatives. But we're going to re-index this so that the power of x matches the index, and we also recover that it starts at index 0. We can also, however, take this expression for y prime right here, and if I multiply it by x, immediately the power x to the I now matches the index. However, it doesn't include every term. But observe that if I equals 0, this would just give me a 0 anyway. So I can reinsert I equals 0 into this power series without changing anything. The only difference between these two power series is the single term of I equals 0. However, when I equals 0, this spits out a 0 anyway, and adding a 0 is fine. So if I add in that extra term, I get another power series starting at index 0, whose power of x matches the index I. So we've determined that if we assume y has this power series representation, then y prime can be written here and xy prime written like this. And notice that all terms here have an x to the I, where I is the index of the sum, and also conveniently, the index in all three cases goes from 0 to infinity. So I can add all of this up. X, y prime, 3y. Well, all of those will have an x to the I factored out. Here is what I got from my xy prime. Here is what I got from my y prime. So overall, these two terms account for xy prime plus y prime. And now looking at our original power series for y, if I just have 3y, I end up with a 3ai x to the I. So by adding up xy prime, y prime, 3y, we have three different power series that all have a shared factor of x to the I. Factor that out. What's left behind is our y prime, our xy prime, and our 3y. So iai plus I plus 1ai plus 1 plus 3ai x to the I, which we can simplify as the two terms with ai, an iai and a 3ai just becomes I plus 3ai, plus I plus 1ai plus 1 x to the I. So here is our power series for x plus 1y prime plus 3y. A single power series, all times x to the I, index going from 0 to infinity. However, in this problem, x plus 1y prime plus 3y is 0, so this power series is 0. The only power series that is 0 on an entire interval has all 0 coefficients, and since we centered the power series at an ordinary point, we know that it has a positive radius of convergence. So if it's converging on an interval to 0, every coefficient must be 0. Therefore, I plus 3ai plus I plus 1ai plus 1 must always be 0. This allows us to solve ai plus 1 is negative I plus 3 over I plus 1 times ai. So therefore, any solution as a power series centered at 0 has coefficients ai that satisfy this recursive formula. ai plus 1 equals negative I plus 3 over I plus 1 times ai. We're going to compute a few terms and hope that a pattern emerges. So a1, by setting I equals 0, a1 is negative 3 over 1 times a0. a2 is negative 4 over 2 times a1, and we're not actually going to simplify that. If I plug this in for a1, then the negatives cancel out, and our numerator is 4 times 3, and our denominator is 2 times 1 times a0. a sub 3 would then be negative 5/3 times what we just found, making our numerator 5 times 4 times 3, and our denominator 3 times 2 times 1. So the numerator and denominator seem to be building up products that kind of look like factorials. But the product in the numerator didn't include all the integers counting down. Okay, it was 3, then 4 times 3, then 5 times 4 times 3. So the product doesn't include the 2 or the 1, but it also didn't just stop at the index I, it actually went to larger. For index 1, it stopped at 3. For index 2, it was 3 times 4. For index 3, it was 3 times 4 times 5. So we might speculate that the denominator is building up nice normal factorials. That seemed to be what we were getting. But the numerator is actually building up I plus 2 factorial. However, it is not getting the 2 or the 1. So divide out 2 times 1. So our denominator is hopefully I factorial. It was just building up 1, then 1 times 2, then 1 times 2 times 3, and so forth. But our numerator was building up a 2 larger factorial without the 2 or the 1 in it. So we will attempt to show in general that ai always matches, well, it was alternating sign, so negative 1 to the I. Here's what we think our numerator is, here's what we think our denominator is, and that simplifies as follows. Here, the 2 ends up in the denominator. Also, I plus 2 factorial over I factorial cancels a lot of terms and leaves behind only I plus 2 times I plus 1. So we suspect a sub I is always given by this times a sub naught. So we have a claim that ai is always this expression times a naught. For I equals 0, this does just reduce to a sub 0 equals a sub 0. Negative 1 to the 0 is 1. 2 times 1 over 2 is just 1, and you just get a naught equals a naught. That's definitely true. Our base case is trivially true. So let's assume that ai does match the form above and use the recursive formula that we already found. ai plus 1 is negative I plus 3 over I plus 1 times ai, and hope that assuming ai takes the desired form up here, plugging that into this recursive formula will show that ai plus 1 also takes the desired form. Well, we have negative I plus 3 over I plus 1, and here's ai. It's all of this times a naught because we assumed that it did match the desired form. Now, the I plus 1s cancel out, and I get I plus 2 times I plus 3. And this is exactly what our formula would specify for the next index. We had a negative 1 times negative 1 to the I, so we get negative 1 to the I plus 1. I plus 3, I plus 2 over 2. And since we increased the index here by 1, we weren't trying to get I plus 2, I plus 1. We were trying to get I plus 3, I plus 2, and we did. So we've established that ai always takes the form negative 1 to the I plus 2, I plus 1 over 2 times a naught. Therefore, our power series y is equal to ai times x to the I. So whatever the solution is, it takes this form right here. Now note, if a naught is 0, then every term in the power series is 0, and that does converge for every x, because now we're turning our attention to finding the interval of convergence. Otherwise, we're just going to apply the ratio test. There are other tests we could do here, but since there's an x to the I, a ratio test is going to be pretty quick. So we take the limit, as I tends to infinity, of the ratio of all of this with I plus 1, so negative 1 to the I plus 1, I plus 3, I plus 2, a naught x to the I plus 1 over 2, divided by all of this here. The 2's will cancel, and we'll end up with this expression down here. The a naughts cancel out. I plus 2 over I plus 2 cancels. Since we have an absolute value in the ratio test, these negative 1s to powers don't really matter, and we're really just taking the limit, as I tends to infinity, of I plus 3 times x over I plus 1, all in absolute value. However, that limit is just the absolute value of x. That's a constant that factors out of the limit, and then I plus 3 over I plus 1 tends to 1. So, according to the ratio test, this power series converges whenever the absolute value of x is less than 1. It diverges whenever the absolute value of x is larger than 1, but for x equals plus or minus 1, it's a little unclear. So the radius of convergence is 1. The series definitely converges for every x in between minus 1 and 1. What about those two endpoints? We have to test them manually. Well, if x is equal to 1, then x to the I is always 1, and then the series just becomes this right here. Since a naught isn't 0, by the divergence test, I have a non-zero constant, and as I tends to infinity, this is not converging to 0. So by the divergence test, this series will not converge. So when x is equal to 1, this series diverges. What about when x is minus 1? Well, in this case, x to the I becomes negative 1 to the I, but now I have a negative 1 to the I times negative 1 to the I. Those cancel each other out. They multiply to just be 1. But again, the divergence test, since the general term here, I plus 2 times I plus 1 over 2 times some constant a naught, is not converging to 0. It's going to infinity, in fact, or minus infinity if a naught is negative. So by the divergence test, this series also diverges. So overall, we found our power series. If a naught is 0, it converges everywhere, kind of stupidly. But if a naught is not 0, it converges exactly on the interval from negative 1 to 1, not including either endpoint. As our third example, let's do an initial value problem. Suppose y of 0 is 2, y prime of 0 is 0, and we have the differential equation. x squared minus 1y prime plus 3xy equals 0. Find a power series solution centered at 0. As we've had in the previous examples, the center of our power series is not a root of the leading coefficient. So we're at an ordinary point. Also, the radius of convergence of our power series solution will be at least as large as going to the next root of the coefficient. So we're centered at 0. 1 is definitely a root of x squared minus 1. So the distance there from 0 to 1 is just 1. So the radius of convergence of our power series solution will be at least that large. It will be at least 1. So we start by setting a power series for y centered at 0. Nice standard form. Y is just the sum of ai x to the I. Having assumed that y is just the sum ai x to the I, we start computing various terms that will go into our differential equation. For example, we need 3xy. So if I take this power series, I multiply everything by 3x, we get a 3, but we also increase our power of x by 1. We always want the power of x to just be x to the I. That way, when I combine all terms eventually, I can factor a shared x to the I out of everything. So I re-index this series here. Notice it starts at 0, but the first power is then going to be 1. When I is 1, the next power is 2, and so forth. So if I want the power of x to match the index should start at 1. The first power was the first power that I got here, so I'm going to start this at 1. However, a sub I here, this index was 1 less than this power. So if this power is going to be I, this index is going to be I minus 1. So 3xy can now be written as a sum where the index goes from 1 to infinity of 3 times ai minus 1 times x to the I. Okay, this was our original series. We've come up with a suitable series representation for 3xy, but now we have to work on this right here. Well, y prime we've done before. The constant term for I equals 0 disappears when I take a derivative, so this series now starts at the next term of 1. Otherwise, I just apply the power rule. But again, I want the power of x to be exactly the index of the sum. When I is 1, this begins at power 0. So I can have a series beginning at index 0 where x exactly matches that x to the I. However, this I and this I are 1 larger than this power of I minus 1. So if this power is going to be I, then both of these get shifted to be I plus 1. So now I have a power series representation for y prime, where I have an x to the I that will eventually be factored out. But what about x squared y prime? Well, if I start from here, here was y prime, and I simply multiply by x squared, I just raise the power of x by 2. And now I ask, I'd like to re-index this so that I just have an x to the I. When I is 1, this starts at power 2. So let's start the series at index 2 and have that be exactly the power of x. But now this I and this I are 1 less than this power. So if this has been shifted to just be an I, these must be shifted to be I minus 1s. So we have found the following two series for y prime and for x squared y prime. Ultimately, I want to take the one for x squared y prime and subtract y prime. But these two series start at different indices. So I can't just go ahead and say, take this and subtract that without worrying about where the indices are. However, this sum right here can begin at I equals 1 without changing anything, because the predicted formula here, if I plug in I equals 1, would be 0 anyway. So I can make this series start at index 1, and that's fine. But I can't actually make it go from index 0, because I'd get a negative 1 times a sub negative 1. So we're going to manually split off one term of this series here so that this is now going to be a single term plus all the rest starting at index 1. Then I will be able to add and subtract these two against one another. So putting together some of those steps, here's y prime as the power series we found. Now for I equals 0, we get 1, a1, the constant x to the 0, or just a1, plus all the other terms from index 1 going on. So here the sum starts at 0, here it starts at 1, but we have manually added the term corresponding to I equals 0. So this is the same sum that we had. We already determined this series for x squared y prime. and remarked that if I is 1, it would have predicted a 0, so we can add that term in with no change. So now x squared y prime and y prime both have sums beginning at the same index with matching powers of x. So I can take the difference. If I take this power series and I subtract this, we get negative a1 hanging off in the front, and otherwise we'll get I minus 1 ai minus 1 minus I plus 1 ai plus 1, all times x to the I. So x squared minus 1 y prime is now written as this here with this extra minus a1 hanging around. So we already have this power series for x squared minus 1 y prime. It's a nice power series. There is, however, this minus a1 hanging off on the left. Now, what would that sum predict for index 0? Well, if I were to set I equals 0, we would get negative 1a1 plus negative 1 a sub minus 1 all times x to the 0. Now, a sub minus 1 isn't really a term in our original power series. Our original power series was the sum of ai x to the I beginning at index 0, which means if we simply assume that a sub minus 1 is 0, then I can ignore that term. And this expression for index 0 would predict exactly negative a1 times the constant x to the 0, which is exactly what was hanging off here. So if I just make the assumption that a sub minus 1 is going to be 0, then this formula exactly matches negative a1 if I simply include index 0 in the sum. So we don't need that term hanging off on the end. If we assume a sub minus 1 is 0, since it wasn't a term in the original power series began with a sub 0. So this isn't really affecting our solution. I can give it any value I want. I give it the value 0, then this expression here exactly matches x squared minus 1 y prime without needing to have this thing hanging off on the end. So here's our power series for x squared minus 1 y prime. Here was our power series for 3 times x times y. Now notice this power series begins at index 1. What would it predict for index 0? If I tried to put index 0 into this sum, I'd get 3a minus 1 x to the 0. And since we already declared that a minus 1 should be 0, we can freely add this into that power series without changing its value. So what do we have so far? Here is our power series for x squared minus 1 y prime. It began at index 0 by making the assumption that a sub minus 1 is just going to be 0. Here is our power series for 3xy. It can also begin at index 0 using the same assumption that a sub minus 1 is 0, which means I can just add these two things together, and that will give me my differential equation here, x squared minus 1y prime plus 3xy. Now, if I add these two things together, notice I'll have this times ai plus 1. However, I'll have I minus 1 ai minus 1 plus 3 ai minus 1. That gives me I plus 2, ai minus 1. So here is a power series for our differential equation. Again, with that assumption that a sub minus 1 is 0, I am free to start this at index 0. So now we have this power series expression for our differential equation. For the differential equation to be 0, the series here must be 0. Since we are at an ordinary point, we have a positive radius of convergence, so every term must be 0. So if every term of the power series is 0, those coefficients must be 0. This allows us to solve for our recursive formula. ai plus 1 is simply I plus 2 over I plus 1 times ai minus 1. But notice there's a difference of 2 between these indices, I plus 1 and I minus 1. Those are 2 apart. Therefore, we need to know 2 initial terms before we can deduce the rest. So here is our recursive formula. ai plus 1 is I plus 2 over I plus 1 times ai minus 1. This recursive formula will now help us determine what the coefficients are in our power series representation, y equals the sum of ai x to the I. Now, what is a1? According to this, a1 is 2 times a minus 1, and we've already assumed that a minus 1 has to be 0. So by setting I equals 0 into this recursive formula, we get that a1 had better be 0. a3 is then going to be 4/3 times a1, which is also going to be 0 because a1 is 0. A5 is then going to be 6/4 times A3, but having determined A3 is 0, this must also be 0, and so forth and so forth. So it certainly seems that our assumption that A minus 1 is 0 actually forces all of the odd indexed AI to all be 0. But what about the even ones? Well, A2, if I set I equals 1 here, I get A2 is 3/2 times A0. A4, by setting I equal 3, is 5/4 times A2, but A2 was this, so we get 5 times 3/4 times 2 times A0. A6 will reduce to 7 times 5 times 3 over 6 times 4 times 2 times A0. So what we can deduce pretty quickly and prove inductively is that indeed all of the A sub odd numbers are 0, and the A sub even numbers are this product beginning with an odd number, going down by 2's, ending at a 3 times 1, over this even number, and the product goes down by 2's, and then times A0, whatever that was. So we can now write our series as, here was our original series for y. First, we break it apart into all of the even indexed terms plus all of the odd indexed terms. All of the odd indexed terms are 0, so really all we have are the even indexed terms, and a sub 2I follows this formula right here, so we just plug that in. So here is the power series solution for y. So we found this power series solution for y. The initial value y of 0 equals 2 tells us that a sub 0 equals 2. Remember, in our power series, we have y is a0 plus a1x plus a2x squared plus a3x cubed and so forth. Plugging in x equals 0 makes everything vanish except the constant term. So the constant term must be 2. Therefore, a0 is 2. We're not going to cancel it from the denominator, however, because this 2 in the denominator is a nice kind of thing to have for this formula. Take an even number, go down by 2's. So we're just going to leave it there as an extra factor of 2. So we have this product of all of the odd numbers up to 2i plus 1 divided by a product of all of the even numbers up to 2i times 2 times x to the 2i. Now we actually never used the initial condition that y prime of 0 was 0. That was in here as one of our initial conditions, and we haven't used it. Indeed, if we had let x equals 0 in the differential equation, we would get negative y prime of 0 plus 0 equals 0. Then there would be no solution at all. If y prime of 0 was anything other than 0, then this line here couldn't have been true. So this information that y prime of 0 is 0 wasn't really useful to us. It was absolutely necessary for a solution to exist at all. Okay, so y prime of 0 is also a1, and we've already determined that every odd indexed ai must be 0. So indeed, the first derivative at 0 had to be 0. That wasn't really helpful information. So it's definitely true, but we never actually used it to find our solution. Also, since we do have a first order differential equation here, typically an initial value problem would actually give us just the value y of 0 and not give us y prime of 0. That was extra information. There was only one possible value it could ever take. So altogether, what have we done in this rather long video? Power series give us new ways to find solutions to differential equations. Specifically, when we have a homogeneous linear equation with polynomial coefficients, and we are centering our power series not at a root of the leading coefficient. In other words, we're centering the power series at an ordinary point of the differential equation. Well then, the differential equation itself leads to some new power series. Whatever terms we have, x times y, x squared times y prime, whatever, we have to figure out power series for those, re-index them so that they all have a shared factor of x to the I so that you can combine them into a single new power series that is a bunch of stuff times x to the I. Homogeneity says all of this equals 0. Therefore, all the coefficients are 0. You're then going to get a recursive relationship on the coefficients of the original power series, something about finding ai plus 1 if you know ai, for example. You can frequently then factor out some arbitrary constant, like what is the constant value a sub 0, and leave behind a nice explicit solution to the differential equation. It takes practice, it takes work, but it's a very powerful technique to solve equations that we might not otherwise be able to do. Now in this video, we only did first order equations, and those could have been done using techniques of separable differential equations as discussed at the very beginning. However, we will shortly see that we can solve second order linear differential equations using these techniques as well.